let's look at the derivative from L to any particular location on this neural network here, right? Be it a node or be it a weight. So let's just like the derivative of L with respect to, I'm going to just call it R for some R. So R may be one of these nodes. R may also be one of these weights. So we have a summation from the path P that is in a member of the paths from L to R. So that gives us each path. And then how do we compute the gradient for a particular path? We multiply together the gradient for each individual element of the path. So we are now going to multiply, right, the product for every segment that is from S to T in the path P. And this will then just be the partial derivative of S with respect to T. So what do I mean by here? Well, if we look from L to W1, we have a top path and a bottom path. Within that top path, we have a bunch of segments. We have the LJ segment, the JI segment, the IF segment, the FE segment, the EB segment, the ABA segment, and the AW1 segment. And so we're going to just take, this is going to basically turn out to be a product of from L to J, J to I to F, F to E, E to B, B to A, and A to W1. But it's this structure that I want you to notice. This structure that we have a summation of products, of gradients for particular segments along the paths. So what does that say? Let's look at this for a second. Well, first thing it says, if we have got any individual segment that has a gradient of 0, then the gradient for that path is 0. For example, if this ReLU, if the output of G were negative, then the derivative, partial derivative of H with respect to G would be 0, right? Because it would be on this flat part of the ReLU curve, the left part of the ReLU curve. And so therefore, this entire path would turn out to be 0, because again, if we have the product of a number of things and any one of them is 0, then that's 0. So that's one thing to note. A second thing to note is what happens if you've got a lot of small gradients. So let us compare ReLU to tanh. So tanh looks like that, and ReLU looks like that. What's our maximum gradient in ReLU? 1. Basically, it's either 1 or it's 0. What about tanh? Well, tanh, if the input is large or the input is small, right, big negative or big positive, then the gradient becomes close to 0, right, because we're asymptoting to 1 or negative 1 here. So there's only a small range where we've got a useful gradient. Now, it is true we have also got the gradient where we're looking at the weights. So we're also multiplying by the weights times a bunch of different W's. For various W's in here, right? If we're going along the bottom, this W and this W and this W and so on. Right? What can happen though is we can end up with what's called vanishing gradient. And that just means that the gradient becomes small. The total gradient becomes small. And why does it become small? Well, what we're saying, in order for it to be small, we need to have basically every individual gradient, every gradient of each path be small, ignoring, I suppose, cancellation of positive and negatives. Right? So you'd certainly have vanishing gradient if you had every path had a 0 gradient. You'd also have a vanishing gradient if every path had a very, very small gradient. And how can we get small gradients? One way you can get small gradients is if we have small derivatives of the activation functions. So using tanh, it's very, very easy to get this vanishing gradient, where, yes, you can get some reasonable gradient that is updating these weights, and a little less for 2 back from the loss. But once you go in deep, just means there's basically no change that's happening to W1 or W2 or W3 over 4 for training. So one of the changes that was made that has made deep learning successful, that is deep learning meaning the deep neural networks, was changing from using a tanh activation function to a ReLU activation function. And the ReLU is much better because of the fact that it's like a gate, right? The gradient is either completely open, where we have a gradient of 1, right? So the gradient is fully moving through, or the gate's shut and it has a gradient of 0. But if the gradient is moving through, it's completely moving through. And so we'll have a bunch of 1s, and so therefore we should get a non-zero gradient. Unless the weights are small. If weights themselves are very close to 0, we're multiplying a bunch of weights together, and that again can cause a vanishing gradient. So some of the advances in deep learning have really been appropriate activation functions, okay, ones that have a reasonable derivative, so that we have a gradient not substantially less than 1, and also better initialization and knowledge of the weights, so that the weights don't get too small either. It's important to note when we have a vanishing gradient that in order to have a vanishing gradient, that requires that every single path have a small gradient. Okay? If we have even one path that has reasonable gradient, then we're going to be able to update that parameter, right? Because we'll get whatever that one path, we'll find it, and we'll get that gradient. All the rest may be 0, but we'll still get a non-zero, and then we'll be able to update that weight. We've talked about gradients along this path that are less than 1, and what a problem that can cause. But if their magnitude is much greater than 1, then we have another problem, right? Another problem really has a similar name, so this is exploding gradient. And this is where basically the gradient overflows. Or is just so large that the weight, after a few iterations of updating quickly, overflows. So that's going to commonly happen. It can't be a problem in ReLU, right? The activation function itself, it isn't a problem because we, again, just have a gradient with the perfect value of 1. But if we have weights that become large, let's say we have weights that on average are, let's say, 5, okay? Then as we go down, we're going to get some 5 to the n factor here, right, in our multiplication. So our product is going to give us a factor of 5, another factor of 5, another factor of 5. If we've got any of those, that's 5 to the n. That becomes a pretty big number pretty quickly. And if we keep in mind ResNet, for instance, as what, 134 is a reasonable depth of that. So 5 to the 134, a big number. That's the exploding gradient. How many paths have to have a large gradient for the entire gradient to be large? That is, how many paths have to explode for the entire thing to explode? Just 1. Because basically if one of them overflows, then we're summing together an overflow value with a lot of other values, and that continues to be an overflow. We will look in the future at some ways of avoiding exploding gradients. It's in some ways a little easier to deal with than vanishing gradients. So for exploding gradients, one quick fix is just have a clip. That is, just say, if the gradient for any particular path is more than some value, just cap it at that value or clip it at that value. So that's called a gradient clipping. So exploding gradients can be addressed with gradient clipping. The vanishing gradient, well, one thing that can help with that is if you don't have the ReLU completely cut off the gradient moving through. So that's the idea of the leaky ReLU. So we still have a kink, but here we're something like, right, this one is max of 0x. This one would be something like max of, we don't have some constant here, some hyperparameter. I'm just throwing a constant. So let's say 0.1x. So that the gradient is either 1 or it is 0.1. And so therefore, in either case, we've got some gradient that's moving through back to previous nodes in the network. In deep learning, we have this Goldilocks situation. We want the gradients to be just right. We don't want them to be too big, and we don't want them to be too small. In order for that to work, we need to make sure that the gradient through the activation function is not too big and not too small. And then we've got to make sure that the weights are not too big and not too small. It's a delicate balance, and it's easy to see why there were so many difficulties in having deep neural networks. Right? It wasn't just a matter of lacking the computational power in order to be able to do deep networks. It also had to do with the fact that the gradient just kind of died out normally or exploded. So either shrank down or exploded, and therefore we couldn't successfully update networks, even of size 10, let's say, right? So 2 was about the limit of what you could easily update without any problems.